Here we're going to continue our discussion of two-component systems, looking at phases and equilibrium and so on. Here we're going to talk about liquid and gas components. In Lecture 11 we talked about two liquid components. All right, what happens when you mix a liquid and a gas in terms of phase behavior? And by the way, these gas-liquid mixtures typically are not ideal. Well, what William Henry back in 1803 found was that the pressure of the gas above the solution is proportional to the mole fraction of the gas in the solution. So if we go here, let us draw our prototypical system, a closed system here. Here we'll have some liquid down here, we'll call that component 2. Here we have a gas, we'll call that component 2. That's the vapor, so there's an equilibrium between the two. This is a single component system. Now let's add a gas above this solution here, and we'll call that gas component 1. What will happen is a gas will equilibrate and dissolve in the liquid, so now you have this equilibration occurring along with this equilibration. So what Henry found was that the pressure of this gas above the solution was proportional to the mole fraction of the gas in the solution. So if you double the pressure, you double the concentration. And the proportionality constant is usually given the symbol lowercase k, and it's particular for a particular component, and also depends on temperature. Now what I did in my spare time was that I went and actually looked up the original paper published by William Henry, Experiments on the Quantity of Gases Absorbed by Water at Different Temperatures and Under Different Pressures. It was published in the Philosophical Transactions of the Royal Society of London way back in 1803. So here it is. And this paper was read December 23rd, 1802. Back then you would write up a paper and then you would actually read it in front of, in this case, the Royal Society of London, and then they would publish it. So let's find the statement in here of Henry's law. And here it is on page 42. It says, water takes up of a gas condensed by 1, 2, or more additional atmospheres a quantity which ordinarily compressed would be equal to twice, thrice, etc. the volume absorbed under the common pressure of the atmosphere. Well, back then they had a different style of writing, and this doesn't really say very clearly what we had claimed Henry's law was, but if we parse it out, maybe we can figure it out. So let's see, water takes up, okay. A gas condensed, that must be increase in pressure, so increase the compression by 1, 2, or more additional atmospheres. All right, the water will take up a quantity which would be equal to twice, thrice the volume absorbed under the common pressure of 1 atmosphere. So that sort of says that the amount of the gas in solution is proportional to the pressure of the gas above the solution. Well, anyway, there's a couple other funny things, not funny, but interesting things to read here. Here's one of them. So Henry had to build an apparatus. You just couldn't go to the chemical stockroom back then. You had to build your own apparatus. And so he says that the apparatus, however, I have no doubt, may be greatly improved. But at the distance of nearly 200 miles from the metropolis, presumably London, I was under the necessity of using such a one as I can be constructed by my own hands. That would be equivalent to you're doing some research in Binghamton and you want to do some experiment. It requires a particular kind of apparatus. The specialized tools would be in New York City, but you couldn't travel there because it was 200 miles away, and you had to build the apparatus here in Binghamton with your own hands. Such were the trials of trying to do experiments back then. And here's another interesting thing. Since my paper was printed, I have found the numbers assigned to it, etc., are rather below the truth. So that's an unusual thing to write in a paper. Nowadays, can you imagine some researcher, after presenting some data, then saying in appendix, oh, by the way, those numbers I just presented are rather below the truth. That's sort of interesting. Anyway, I'll post this paper on Blackboard in case you're interested in reading about it. All right. Turns out that we can extend Henry's law, which originally was formulated just gas equilibrium between the gas above the solution and the gas dissolved in the solution. Let's extend that to liquid components. So this is what we talked about in the last lecture. We have liquid component 1 and liquid component 2, and these are in equilibrium with gas component 1, and this is in equilibrium with gas component 2. And here we have two gases, just as we did here, but in solution there's the liquid and the gas. Here it's liquid and liquid. And as we said in lecture 11, most liquid mixtures are not ideal. That is to say, they do not follow Raoult's law. Let's look at some data that okay, here's some data. This figure is taken out of the Atkins and DePaula physicochemistry textbook. What we're plotting here is like a typical Raoult's law plot. We have pressure here versus mole fraction of something, and there are two lines. One is the partial pressure of one component, which is acetone, and the other line here is a partial pressure of chloroform. If these two components followed the ideal mixture, then these lines, partial pressure, should be linear. That'd be Raoult's law. The actual data, these dots here with the line, fall below Raoult's law. So therefore, this system, acetone chloroform, exhibits negative deviations from Raoult's law. And let's look at here, this is mole fraction of chloroform. So at 0 chloroform, you have pure acetone. So this pressure above the solution is just the partial pressure, or the vapor pressure of pure acetone. Similarly, over here, you have 100% chloroform. The vapor pressure above that solution would be the vapor pressure of pure chloroform. All right, but let's look at limiting behavior. At low concentration of chloroform, which we had a discussion earlier, we'll call that the solute. So when chloroform is at low concentration, that's a solute, and acetone would be the solvent. But now as you increase chloroform concentration, over here, chloroform ceases to be a solute. Now there's more of it, and now it's a solvent, and acetone is a solute. So here's the chloroform curve. Let's look at low concentration of chloroform, where chloroform we're considering as the solute. What you find is that at low enough concentration, you get a linear function, starting at 0, linear, which means that the vapor pressure of that component above the solution is proportional to the mole fraction in the solution. That's just Henry's law. Another way to look at that is you draw a straight line tangent to the data at low concentration. So that's just Henry's law. So at low concentration, where now we're considering the solute, the vapor pressure above the solution is proportional by Henry's law to the concentration in the solution. Now let's look at high concentration of chloroform. Now we're in the solvent regime. You find that the data always approaches Raoult's law at high concentration. So up here, we'll have Raoult's law holding. So at high concentration, where now we're considering the component to be the solvent, we'll have the vapor pressure above the solution is proportional to, but Raoult's law, the proportionality constant, is the vapor pressure of the pure solvent, or pure component, times the mole fraction of the component. So this is Henry's law, and this is Raoult's law. And they're both of the same form, but they have different proportionality constants. Let's look at the ratio of P1, the vapor pressure above the solution, divided by the concentration in solution, the mole fraction in solution. So if you look up the Wikipedia article on Henry's law, they have a nice way of summarizing that. We're going to look at the ratio of the pressure above the solution to the mole fraction in the solution. And we're going to take the limit as the mole fraction approaches 1. So we get high concentration. What you get is this proportionality constant is just the vapor pressure of pure substance, pure component. So this is Raoult's law. On the other hand, if we take the other limit, P1 over X1, the limit as X goes to 0, so now we're going to low solute concentration, this is just equal to the Henry's law constant, K1. All right, so that's a neat way of summarizing those things. All right, so that's it for this part of the lecture. Now we'll continue on in lecture 12b.